A warm welcome to all the viewers. Friends, in this video, I am going to discuss about regression and multi-level modeling frameworks. So I am going to discuss with you what is GLM, LMM and all these models listed over here. What are the fundamentals of applying these kind of techniques, why they are used and why they are so important. So let us start. First, we have to understand that how these things have been developed. Over the years, it has been seen, you all must be aware about simple linear regression, wherein we have one independent variable and one dependent variable. Multiple linear regression, where we have several independent variables and one dependent variable. Multivariate regression, where we have more than one dependent variable. So, after the advancement of techniques, we come to have general linear models known as GLM, which consider several assumptions to be fulfilled in order to execute the analysis. The assumptions being normality of the residuals, continuous nature of the dependent variable, and independence of observations. These are the assumptions. But what to do in case the data exhibits non-normality? In that case, we have generalized linear models. GZ standing for generalized. Mixed models. Apart from the fixed effects, which you want to test, fixed effects means the independent variables, what influence they lay upon the dependent variable. That is known as fixed effect. There are certain random effects which affect the relationship between independent and dependent variable. When you include those random effects in the model is known as mixed model, wherein you have linear mixed model, generalized linear mixed model. Later on, structural equation modeling was developed in parallel for the latent variables. In case you have several latent variables, reflective latent variables or formative latent variables, each having their own indicators. In that case, structural equation modeling does a lot of work without paying much of effort. Then we have multi-level structural equation modeling, where you have the first order constructs and second order constructs. It has grown from the combined ideas from structural equation modeling as well as mixed models. Now let us understand what is a linear model. So when I discuss about linearity assumption, you all know the expected value of the outcome has a linear relationship with the predictors. Herein, we ascertain, is the expected value of y a straight line function of the predictors? Is the mean of y correctly represented by the chosen functional form? So linearity assumption, one of the important assumptions of carrying on regression analysis. Actually, we do this linear assumption. We plot on a xy graph wherein y-axis represents the residuals. Residuals means actual minus predicted value, and the x value represents the predicted value. When you plot this, you must get a straight line function. So that straight line indicates that linearity assumption is fulfilled. Now, what is a linear model? A linear model is a statistical model in which the dependent variable is expressed as a linear combination of parameters, that is coefficients. The important point is that the model is linear in the coefficients, not necessarily linear in the variables themselves. The parameters we estimate must appear in the simple additive form not multiplied together, not squared, not placed in exponents or logarithms. Herein you have an example of a linear model. Some people will say that it will give a curved line as it is a quadratic regression model. It is a type of polynomial regression model because this independent variable x is squared. It is geometrically non-linear because of the quadratic term x square, which creates a curved parabola when plotted. But still, you see here, we are not concerned about the variables being squared up or their quadratic effect. As the linear model definition says, that betas must appear in a simple additive form and they must not be multiplied, squared, or placed in exponents or logarithms. So we see here they are added beta naught, beta 1, beta 2. They are simply added together. Let us move ahead to understand what is random effect and fixed effect so that we understand these modeling techniques in a better way. Random effect is a variable that introduces correlation or similarity among the observations because they belong to the same group. It controls for the nuisance that is attributed to grouping variables in order to generalize the results for the population. It is categorical in nature. For an instance, which hotel or which type of hotel, and it produces variance components. By variance components, I mean the model calculates the variance, that is the spread or distribution of the data points of these groups around an overall population average instead of computing individual coefficients for every single group. Now, I'll give you a simple example to understand this better. Does service quality affect guest satisfaction after accounting for differences between the hotels? Say you collected the data from 500 people staying in 20 different hotel properties. So the experience encountered by the guest in a particular hotel, say you took a sample of 20 guests from a particular hotel or 30 guests from a particular hotel, their experience would be quite similar. But collectively, you are analyzing the data of those 500 guests. Now, in order to assess the groups as collective sample taken from the population, we say how much variation exists among hotels overall. So here in this case, we include the type of hotel, which is a categorical variable, as a random effect in the model. And if random effect is included, it is known as a mixed model, as I already told you. Without the inclusion of random effect, if we are just considering the fixed effect, whose specific effect is to be estimated, variables like age, income, service quality, this can be continuous, binary, count, ordinal, or nominal in nature. And it produces regression coefficients. Here, each group acts as its own separate intercept or baseline, and the model calculates a unique beta for each specific category relative to the reference group. So, for an instance, does service quality affect guest satisfaction in specific type of hotels? And we want to compare them. Is Hotel A different from Hotel B? Is Hotel B different from Hotel C? In that case, we include the fixed effect. Now let us see types of models. You see here, depending on the number of outcomes and whether that outcome is normal or non-normal in nature, we can classify these models into different categories. If you have one dependent variable and no random effect, it is known as general linear model. In case you have non-normal outcome, that is non-normal dependent variable, you call it generalized linear model. One dependent variable with random effect, Normal dependent variable, that's the outcome. Linear mixed model, LMM. Non-normal outcome, generalized linear mixed model. Multiple DVs and no random effect, we call it multivariate general linear model in case the outcome is normal in nature. Multivariate generalized linear model, in case the outcome is non-normal, there are several multiple dependent variables but no random effect included. Multiple dependent variables with random effect, you call it multivariate linear mixed model. This is the most complex one. And non-normal outcome in case of multiple dependent variables with inclusion of random effect is known as multivariate generalized linear mixed model. So herein I have compiled in a simple chart for you to easily understand and identify that what kind of analysis do you need for your research. Now, what are the limitations of AMOS or Smart PLS structural equation modeling analysis? Why can't we do these modeling in IBM SPSS AMOS or Smart PLS? So there are four big reasons for that. First is that ordinary structural equation modeling in AMOS or Smart PLS assumes that every observation is independent from every other observation. This assumption is violated here, as tourists staying in the same hotel tend to have similar experiences because they share the same staff, same facilities, and same location. Therefore, the tourists from the same hotel are not independent observations. They are linked because they encounter similar experiences. They are not independent of each other. This is known as hierarchical data. So, mixed models solve this by explicitly accounting for the hotel grouping by inclusion of random effect. Now, what is a random effect? You are not interested. So, mixed models solve this by explicitly accounting for the hotel grouping. Now we come to random effect. The second reason is, if you are not interested in determining guest satisfaction level in hotel 1 versus hotel 2 versus hotel 3 and so on for 20 included hotels, as you have surveyed 500 tourists staying in 20 different hotels. This is a simple example to understand. Then you only want to account for the fact that few hotels generally have higher guest satisfaction level than others. However, AMOS and Smart PLS cannot estimate this random effect variance term. They can only estimate fixed regression paths such as independent variable service quality leading to guest satisfaction. But they cannot assess hotel to hotel variation. Mixed models do this using a random effect, right? Third reason is, or the limitation is, binary outcome variable. Suppose the dependent variable is binary in nature. You are asking the respondent whether you would like to revisit the hotel and give him or her two responses to mark on, yes or no. This is a binary outcome variable. However, linear regression and standard structural equation modeling assume outcomes behave like continuous variables. They need continuous variables as outcome, right? In structural equation modeling. So AMOS and Smart PLS are not designed primarily for this type of outcome, but mixed models use logistic regression, which naturally handles probabilities between 0 and 1 and allows for binary outcome variables. Fourth is count outcome variable. Suppose your dependent variable is number of visits last year. The counts have special properties like they cannot be negative, they are often skewed, and variance often increases with the mean. However, linear regression and structural equation modeling assume normally distributed residuals, which is violated by counts data. So herein, mixed models use Poisson regression and negative binomial regression, which are specifically designed for count-based outcome variable. So these are the four reasons, or you can say four limitations of AMOS and Smart PLS, CBSEM and VBSEM, that we need to consider the importance and use these univariate and multivariate models. Now let us see how to conduct it. For univariate models, that is a single dependent variable which is the outcome, GLM, LMM, GZLM, GZLMM. We have already discussed what do they mean. We have to use the GALJ module in Jamovi, which is quite easy to use. We can do it in SPSS, and we can do it through the linear model GLM and LME4, that is linear and generalized linear mixed models package in R. Whereas linear model and generalized linear model are built into the base R, so they are readily available after installing R. You just need to install LME4 separately to analyze these models, univariate models, which are listed over here. For multivariate mixed models and advanced multi-level models, multivariate GLM, multivariate LMM, multivariate GZLM, multivariate GZLMM. In this case, you have to use the Bayesian regression and mixed models, that is abbreviated as BRMS, which uses the computational engine STAN in R. BRMS is to Bayesian statistics, what LME4 is to classical mixed models. So classical mixed models, univariate models, which we have seen right here, LME4 package is used. And for Bayesian statistics, we use BRMS in R. I hope the video was quite informative and useful for you, and you will definitely share it with your friends and faculty colleagues. See you next time with some more informative content. Thanks a lot.